Hello, welcome to Engineering with Rosie Live. Okay, so this live stream is made possible by sponsorship from WeatherGuard Lightning Tech. So I need to give them a big, huge thank you. They allow me to spend the time that I need to prepare to make these really valuable. They make a lightning protection system called Strike Tape, and it's a protection system that can be retrofitted onto wind turbine blades and aeroplanes to improve on the factory lightning protection systems. I also need to give a big thanks to the Engineering with Rosie Patreon community for their support, and they send questions ahead of the live streams as well. So for this one, especially, the questions that they raised were really interesting and kind of sent me in a different direction to what I was expecting. So actually all of us here today should be thanking the Engineering with Rosie Patreon team for really raising the bar today. Okay, so let's move on to the main event. So today I'm going to be talking about groups of wind turbines. Okay, so I made this community post, and I do know that this is called a wind farm, yes, and this is called a multi-rotor. But I was after a kind of a more catch-all term for it, and I got some good suggestions, like an array, yes, sure, a whirlpool of turbines. I think that's pretty funny. But then I'm such a sucker for a good technology pun. So this one from Cameron Sowers, a fan club, that definitely won the day for me. So from now on, I think we should all call groups of wind turbines a fan club of wind turbines. So the reason that I chose this topic today is because there's been a usual ways of grouping wind turbines in the news this year, and people keep on sending me links to stuff like this wind catching one. Especially my dad keeps on sending me links to this one. Hi, Dad, if you're watching. He was really taken by it, and I have to say that as I investigated it more, I found it more interesting. So I will thank him for that. And then there's also this one that I got sent a lot about vertical axis wind turbines and how if you group them close together, you can get more energy. And with the sometimes it was only implied and sometimes it was explicitly stated that, grouping vertical axis wind turbines closely together is going to be better than horizontal axis ones. So the future is vertical. And there were just that's an interesting conclusion to draw. So because there was so much attention on that study, I wanted to talk about it. So as well as talking about those two items, I'm also going to give some backgrounds about how wind turbines are actually grouped in industry, because I think that one of the main problems with this kind of reporting is that people don't really understand how, like, what the status quo is, what are people doing. So I'm going to be talking a lot about that. And then I also wanted to go up to here. So this is a Vestas multi-rotor turbine, and I wanted to include that today because I actually get told a lot that the reason why nearly all wind turbines look the same, similar with 3 blades and horizontal axis. People frequently tell me that, wind energy engineers have all drunk the Kool-Aid and or we're just, like really unimaginative and can't think any differently to what's, been done for the last 50 years. And so I wanted to give this as a really visible example of one of a major manufacturer who is definitely thinking outside the box and pursuing it. I mean, all the major manufacturers are pursuing innovation. I mean, you have to be, sure that you're going to be producing the right thing in a decade, 2 decades time. But this one was a really visible example. And then just the final image in the post that I did was of a study on wake steering. So these are horizontal axis excuse me. These are horizontal axis turbines, and then they're just looking at altering the direction that they're facing to get better performance from the wind farm as a whole. So overall, there's heaps happening in this space, and I actually found it really interesting researching this, probably more so than I would have thought. I never really considered that wind turbine siting within wind farms was going to be such a fascinating topic, but I have found that it has been. Yeah, so I just want to give my normal disclaimer that everything I talk about is just my own opinion. For this, I did get in touch with a few people whose work I'm featuring. I couldn't reach everyone. I relied probably more on just general contacts that I have in the industry who are really working on, wind turbine siting or design of these, working with these kinds of technical topics. So, I'm not providing any investment advice or financial advice or any formal advice of any kind. If you want formal advice, then you can get in touch with me through my consulting company, Partalite. Okay, so I just wanted to also mention that in the description, I have a lot of links to some of the papers that I read, and there's some more that I didn't get a chance to add yet, and I will add those. Okay, so let's just start with how a wind turbine extracts energy from the wind. So, we all know that wind turbines are taking kinetic energy from the moving air particles, and they are then transforming that into rotating the wind turbine blades, which then via the generator generates electricity. And I actually did a video on this in my early days, so my early YouTube days, which was only about a year ago, but it seems so long ago now. So I just wanted to play this video. I hope that you can hear the audio, but comment if you can't. I did try to. Amount of kinetic energy of that air that passes through the disk is the power, the amount of energy per unit time. So the total power P of air with wind speed V flowing through a disk with area A is given by this equation. The wind that flows through the disk swept out by the turbine rotor comes from way upwind of the turbine and extends way downwind. You can visualize this as a stream tube. And of course, some of the energy is taken out of the air by the turbine. That's the whole point of the wind turbine. We already saw that the amount of energy in the air depends on the mass and the speed of the air. And since the turbine doesn't consume any of the air, every air particle that enters the rotor disk also leaves it. So the mass of the air at any location in the stream tube is the same. So if the air particle's kinetic energy is reduced, but the mass of the air stays the same, then we know its speed must decrease when the wind turbine extracts energy. Since the mass is the same all along the stream tube, but the speed changes, the width of the stream tube changes. It's wider downwind of the turbine when the wind speed is low and narrower upwind when the wind speed is relatively higher. Okay, so that's pretty funny for me to watch that. It's only a year ago, but I feel like I've come a long way, especially with the microphone. I will say to past Rosie, you really need to work on your audio, as hundreds of people commented on those early videos. So thanks everybody for that essential feedback. I also want to show sorry, I'm just going to have to find it. There's one of the papers gives a good description about what's going on with the wake. I think it's this one, modeling and measuring flow and wind turbine wakes in large wind farms offshore. So this whole paper is talking about the fact that when you arrange wind turbines one behind the other, then you're going to affect the turbines behind. And I'll talk a bit more about their results later because it's interesting. But we'll just read their introduction to what the wake is. So as wind flows through a wind turbine and energy is extracted, the volume of air downwind of the turbine has a lower wind speed and higher turbulence than the free stream. And then as it moves downstream, it expands and energy is transferred inwards from the rim such that the difference between the wake air and free stream is gradually reduced. And then the effect on wind farms, the most obvious effect is lower power on the turbines behind and higher loads at the turbines experiencing wakes compared to those experiencing free stream flows. Okay, so that's basically just summarizing the whole issue. And it's not a surprise to anybody, I guess, is the point that I really want to hammer home, which I don't know, it's obvious to me, probably I would guess it's obvious to most of you that, we put a wind turbine in, the whole point is to extract energy out of the air, right? We all know that the air behind has to be slower. So I don't think it would have been a surprise to the first person that made a wind farm if they, put them one behind the other downstream direction, that the one behind would see less wind speed than the one in front. So However, I do notice time and again in articles that I read, and one of them I'm going to go through about new ways to arrange wind farms. They do kind of seem to act like it's this huge surprise to anybody that installed a wind farm that wind turbines take energy out of the wind. Oh yeah. So this paper, it looks at a wind farm. This wind farm, it's Danish. I guess you call it NREL. That's kind of how you say this word in Danish. Pronunciation probably isn't as good as it used to be. So it's just off the coast, the west coast of Jutland. And for those who are interested, this is where I used to live here. And so this is the wind farm, and you can see it basically is kind of like a grid array. And yeah, so you are seeing all of the downstream. No matter where the wind is coming from, there's always going to be some downstream wind turbines, right? So they not only did simulations here, but they actually took measurements. So that's why I found this this study particularly exciting. And somewhere here they have some results. So we see this is the power of each turbine downwind. So this one, number one, this is the one that's hitting the wind first. And then as we go down, turbine 2, 3, 4, 5, 6, 7, 8, that's the ones behind it in the rows. So you can see that in the worst case, this is when the wind's at 270 degrees, and I guess that lines them up in nice rows. We are seeing about a 40% reduction in the downwind turbines in the very worst case. And then this figure here shows from different wind directions. So you can see, yeah, that's really bad for the wind farm when the wind comes from that direction, and then at other directions, it's not as bad. So yeah, I don't know, maybe it's like an 85% reduction on average for the downwind turbines. So I just wanted to mention that this effect, like, it's significant and it's big and people care about it, but it's maybe not as big as it first sounds, because one, it only matters up to the rated wind speed. Once you reach the rated wind speed, then the generators are going at their maximum amount. There's excess energy in the wind that they could never deal with, no matter what they were seeing. So the issue goes away once the wind speed gets high enough. And then there is one other issue aside from the loss of power. You also see increased turbulence in all of the downstream wind turbines that are in these wakes, and that can have a negative impact on the lifetime of the turbines, because you get these turbulent loads which vary a lot, and that's quite a harsh operating environment. So naturally, wind farm developers and operators are very keen to avoid those losses, and siting wind turbines. You don't very often anymore see wind farms where the turbines are just arranged in like really regular grids like that. And I am going to talk a little bit more later about how wind farms are optimized. Okay, so now I'm going to move on to this vertical axis wind turbine article. So there were heaps of articles written about this. There's this one study that was done, which I'll show you. So like all journal articles, it has a very catchy title: Numerical Modeling and Optimization of Vertical Axis Wind Turbine Pairs, a Scale-Up Approach. So I'll just talk about what they actually did first. So they took pairs of 2 wind turbines, mostly. In one case, they did 3 turbines, but for the most part, it was 2. They changed this angle between them. So if the wind's coming in at this direction, they changed the angle between the 2 turbines, and whether they both rotated in the same direction or if they were counter-rotating, so in opposite directions. They did some 2D simulations, which they validated against somebody else's research, so it was a bit different to theirs. So it's not very robustly validated. Like, they didn't actually build the scenarios that they've analyzed here. And then where's the results? So the results here, this is showing in this graph, you see the angle between the 2 turbines across the x-axis, and then the y-axis shows their performance. So where it's 1, you see the same performance from the 2 turbines would be the same as 2 individual ones added together. And where it's higher than 1, then you're getting more performance than you would expect for the 2 individually. where it's lower than 1, then you're getting less. So their very interesting result is that you can actually, by having counter-rotating turbines, so they're rotating opposite directions, if you get the angle just right, then you can see more performance from those than you would expect by just putting the two separately and far apart. Okay, so that's interesting. There's plenty of issues with the study in terms of it could be more rigorous, but I think for like an early preliminary investigation of an interesting effect, I think that's very good. There's nothing really wrong with the study itself as a preliminary investigation into the effect, but they do misrepresent normal wind farms a bit. So we saw in that previous study that in the absolute worst case, where you see turbines just directly lined up one behind each other, you can get up to 40% reduction in power. And so that's kind of what they don't misstate that here, but they are comparing the worst case of a horizontal axis wind farm, and then their results also show that it's just at a quite specific angle that we see improvement. They also see reductions in performance for certain angles of arranging the wind turbines. So there's no problem with the study, but it was taken up by the media, and some quotes were given that I think really extrapolated way beyond what they actually did here. So I'll go back to the article. So it says here, modern wind farms have one major flaw. As the wind approaches the front row of turbines, turbulence will be generated downstream. In other words, a front row converts about half the kinetic energy, whereas the back row, the number's down to 25 to 30%, which I think is also much worse than what the actual study said and what the previous research showed. So it says, each wind turbine is expensive. As an engineer, it naturally occurred to me that there must be a more cost-effective way. And I mean, it's just misstating what the normal kind of way of doing things is, because it has also occurred to every other engineer that's looked at this problem that there's a better way to do it than to literally put them in the stupidest way possible that wastes the most energy. So I will say that it's something that I do find not uncommon in academic papers on wind energy. There's a bit of a split in between academia and industry in a lot of cases. And sometimes they really totally fail to understand how the wind industry works, which isn't necessarily, I wouldn't say that's a criticism of academia, because I do know, when I was doing my PhD in wind energy, of course, I was in academia, and I could not get anyone in the industry to talk to me about anything. So I think it would be nice to see more cooperation between academia and industry, and where you see the best research coming out, it's where there is that, that overlap. So you can get the really, really in-depth study from academia, but combine it with, the way that the world actually works and the kind of problems that are actually necessary to be solved, like the important problems to solve. So what I wanted to talk about next was the fact that usually in these articles, and I mean, this isn't the only article, there's like a dozen at least on this, and they got shared on LinkedIn, and I got tagged in every single one multiple times. So that's why I'm kind of probably paying it so much attention, because I want to have something to point back to next time that I get asked to comment on a study like this, or similar studies are done every few years, and hype to a similar amount, and I guess it just irritates me. So we see more kind of like extrapolation from the study. So, I mean, remember they did 2-dimensional studies of 2 to 3 wind turbines, and I mean, I can show again what their study. This is what their analysis looked like, right? These two pairs, but then when we go to the articles, then we've always got this image of a whole 3-dimensional wind farm. It's just a computer image. I don't know, maybe it looks like it really exists, which is misleading, but more misleading is the fact that they never studied a whole wind farm like this, and they never studied 3-dimensional, and they never validated it against even wind tunnel tests, let alone real world tests. So, I mean, in their study, they still showed that you need to get the angle between the turbines exactly right. So, when the wind is coming from this direction, maybe a wind farm is optimized, but the wind's going to change direction just like it does for a horizontal axis wind farm that's optimized for, one specific wind direction. So I think that this has the exact same flaws that the horizontal axis wind farm does, that they're kind of, trying to contrast against. So they're comparing like the best case scenario for the vertical axis wind farm with the worst case scenario for the horizontal axis one. So, I mean, overall, I think it's a really interesting phenomenon that you can put, counter rotating vertical axis wind turbines next to each other and get a little bit more power. But I don't think that it is a significant effect relative, like it's not significantly different to what's going on with horizontal axis ones. And then I just wanted to mention one other big thing about this study and any other study where you're showing, wind turbines can be packed closer together. It's one thing people commonly raise with vertical axis wind turbines. If I say, I made some videos mentioning that horizontal axis turbines are more efficient, or for now at least, they are all more efficient than any vertical axis ones that actually exist. And people say, yeah, but you could put heaps of them all over the ground. You can put them closer together. And I think that this idea, it shows that people don't understand what the real parameters are that are at play in siting a wind farm. So your goal is to get the overall cost of energy low. This one, yeah, you can see this. I think this is an NREL paper. Here, so it's their 2019 cost of wind energy review, and actually it's a really interesting paper if you are interested in not just how can you make a wind turbine better, but how can we make them cheaper, which is really what everyone in the industry is trying to do. And then if we go, where was I? You go back to this breakdown of the cost of, so this all comes out at the dollars per megawatt hour. This is what the cost components are. So we've got the rotor making up 13.7, the nacelle 23.3, and it changes a bit every year because as turbines obviously get bigger, things change. But the cost of land is tied up in this O&N, operations and management sector here, this yellow one. And then I did also find here this one study about the cost of wind energy in the US. Here I could find a couple of people had given their land cost. So out of that 30% that was operations, then we see the land, it makes up this proportion of that. So per megawatt hour, it's like $5 from this one respondent and for $4.20 for another one. So it's not the cost of land is not as big a driver as many people think. So that's the first point I want to get at. And then the second point, I talked to a friend of mine who works on wind farm optimization and the optimization of the siting of wind turbines within a wind farm. And he mentioned to me that the land, it's not, you don't like buy a farm and use it exclusively for a wind farm, right? You lease access to the land to put your wind turbines on, and generally the farmer is still got his sheep or whatever underneath the wind turbine. So you lease it on a per turbine cost, or maybe you pay a bit more if you've got a bigger turbine on there than a small one. But the issue isn't the number. It's not the amount, it's not the area of land that you've got, it's the number of turbines that's on it. And so he said that in most cases, the biggest issue with requiring a larger amount of land is that you've got more land, you're more likely to have more land holders that you have to negotiate with. That makes it difficult. So I just wanted to point out that this, it just because you can pack more, say you can pack more vertical axis wind turbines into a site, then that only matters if your land is constrained. So, if you need to clear your land and put an access road into every single one of a bunch of small turbines, that's probably going to be more expensive than if you just have a few big ones with, one road per turbine. I think offshore it will probably be different, but I don't actually know precisely how they lease it's not land, how they lease the water when they put in an offshore wind farm. Okay, so I just want to take a look at a few questions now. So let's see what we've got. Quite a few. So sorry, it's been a while since I went and had a look at them. Okay, so from Eskil Eriksson, the airplane industry has taken up wingtip ailerons to minimize wingtip vortexes. Why never wind turbines? Some of them do, and that is a topic that I'm going to talk about in a future. I have a guest lined up who's a wind turbine blade aerodynamics expert, and so we're going to talk about that then. So I won't talk about it a lot now. Okay, I think from Christopher Sylvia, I think the turbine height is generally set by the blade length plus the safety factor. I don't think there's any reason to have a utility scale turbine on a very tall tower. Yes and no. It depends on a lot of things, actually. In general, the higher the tower, the higher the wind speed. So people want taller towers. And then also, as you mentioned, you want, the longer your blade, the more swept area, so the more wind you can capture. So you definitely need to have your tower that's taller than your blade plus the safety factor. That's correct. If you could, you would make towers super high. You'd make them hundreds of meters high if you could, but there's one structural constraints mean that, it'll be expensive to make a tower that high. And then more commonly, the constraint is that you can only get approval for a certain height of the tower plus the, the blade in the 12 o'clock position. So that's usually what's limiting the turbine heights. But you would generally want that to be as high as possible to reach the best wind. Okay, so Richard Newton says, do they model these problems on computers, or do they use models or real turbines? They do all of that. That vertical axis paper, this one, it's just two-dimensional computational simulations. They do refer to somebody who tested in a wind tunnel, something that was similar. So that would be an example of the middle option where they're using a model in a wind tunnel. And then this one, that the first paper that I talked about here, they've gone to a real wind farm and they've taken real measurements. And I believe that they also compared that to a bunch of simulations, so that, or maybe it wasn't this one. No. In another paper anyway, they did they do a combination, because the more that you have, real world measurements compared to simulations, then you can feel more confident to use the simulations where you don't have that exact wind farm to compare to. So yeah, a combination of all those three things. Obviously, the best is that you have all of it, but it's pretty expensive to put a wind farm up just to test if your simulation was right. So you necessarily end up having to do a bit of a combination. Okay, so from Edward Como, sorry if I said your name wrong, I'm sure I did. Referring back to Christopher, so there could be some efficiency gain, but offset by higher cost of mass production, design stresses, etc. And yeah, you've hit the nail on the head there. It's all a giant multidisciplinary optimization problem, which all of anything to do with wind turbines is. There's just everything affects everything else, and it's really hard to optimize because there's just so much going on. Okay, from Philip Sheridan, is there much turbulence from the tower section compared to the blades? There is. For the downwind turbines, I think no, that the tower wouldn't be the problem. It would be the blades. And I'm going to show you some pictures of what a wake actually looks like in a minute. But for the blades themselves, if you put the blades of if you take one turbine and you put the blades on the downwind side, so the wind hits the tower before it hits the blades, then you get big problems with turbulence on the blades. And that's the main reason why they put the blades on the upwind side of the tower. And I do have a whole video on that. I'll link it in the description for people who come back to this later. Okay, from Christopher again. Sylvia, how much does wind direction really vary in practice? Is the wind direction often one way, or does it vary all 360 degrees? That is a really good question, and it varies. In some places you have wind that's nearly always in exactly one direction, and in those cases wind farms, they basically just like line them up in a row so that they can be incredibly close together, and if the wind always comes from one direction, then they're never going to be in each other's shadow. But more commonly you'll see on one of these, more commonly you see in a bunch of different directions, and this is the way that they kind of graphically represent what a certain site's wind looks like. So this is called a windrose, and it shows the wind frequency distribution. So it was for that study. I think it's the same study that looked at the which wind direction gave the biggest reduction in power in downwind turbines, and so that's that 270-degree angle is the. Actually, this shouldn't be associated with that, because if it was, then that wind farm would be designed in the exact worst way that could be. So in this windrose, we see that most commonly, like 20% of the time, wind is coming from this 270-degree angle. I guess that means northwest. And then you can see the distribution of all the other wind directions. It's got this second most common direction from here. So you can run simulations to optimize the annual energy production. You'd have to run not just one simulation of, the wind going from one direction. You'd have to then, move it a bit and then change it, and then, try and move your wind farm around so that you could get the greatest overall annual energy production. Your second question, is it possible to know the expected wind direction? That they take a lot of measurements. Wind farms are just so incredibly expensive, so they will usually for several years be measuring the wind in the resource that they want. There's also general data available, wind maps. Okay, there's a ton of good question here. I'm going to move on because I'm worried I've actually picked too big a topic for one live stream. I really want to move on to the next thing. Okay, so I just wanted to go to, so this one is a paper about wake model and optimization algorithms selection for wind farm layout optimization. And I just wanted to show what people are doing. We don't just arrange wind farms in grids anymore. They are looking at, there's the windrows, like I mentioned, and then they are locating the turbines within the farm so that, so that you get the best overall performance. So it's really complicated optimization because the wake models, it's very complicated 3D flow. So if you did a really good simulation of that, that's incredibly computationally expensive. Then you've got to do it for all the different wind directions. And then whenever you run an optimization, it means, you've got to run through thousands of iterations of this. So you end up with this just unrealistically large computational requirement to do a real optimization for this. So there's a lot of research trying to figure out ways to get good results without having to, use the whole world's computing power just to optimize wind farms. So this shows how they do it. You take the wind direction and then you allow the wind turbines to move within the farm. Yeah, so in this one, they basically, it was a competition between a bunch of different people that were working on optimizing wind farms. They gave them all the same problem, and these are the optimized layouts. So they started out with turbines just equally spaced in a grid, and then at the end of everybody's optimization algorithm, then this is what they got as their best wind farm layout. So you can see, they're kind of moved around. You get some funny ones where they're all just located on the edge, which is the boundary of the wind farm in that case. So yeah, and they did it with 16 turbines and then 36 and 64. So you see it's really complicated, but and there was also this model that someone shared with me, this Topfarm computer simulation. So you can install this and run this and optimize your own wind farms. It doesn't just optimize for the annual energy production. It also optimizes for, like how can you make the length of your cables the shortest, and road access and everything like that to get the cheapest overall cost of energy from a wind farm. And then I was using it on, you can run it here, but the last time I tried to run it, I got an error. So I won't try to run it. But when you do run it, you can do your own little optimization, and you can see that it's very easy to get like a 30% increase in your annual energy production just by moving around away from the grid design. So, I think that's a good number to compare to like that paper that we were just talking about, the vertical axis wind turbine pairs. So they're fine, like 10-15% increase from putting the turbines in the right orientation. And so we see you can easily get those kind of numbers by really good wind farm optimization if you're comparing to the baseline of like the easiest, stupidest way to do it in just a grid that you're not worried about wind direction. Okay, so I'll just do a couple of questions again. Okay, so this one, I kind of talked about that a bit. Rex Cat 180, do I have any experience with large-scale CFD for entire wind farms? I have certainly not done that myself, but I do know people that do that. There's a business actually based out of here in Canberra where I live called Wind Lab, and they do that. And yeah, like I showed in that paper, that optimization paper, there were a bunch of different research groups involved in that, and all of them are just working on ways to accurately, but not too accurately, model a whole wind turbine's wake to see how to site them the best. From Philip Sheridan, the surrounding topography is probably a factor too. Yeah, it's super important. And when you're locating turbines within an actual wind farm, then you will definitely need to take that into account in that optimization paper that I was just talking about. This is just a flat one because the problem is just, it's so big and so hard to get the problem small enough that you can actually do an optimization. So I don't know, maybe this is a good application for quantum computing. When that finally comes, we'll be able to finally like actually optimize every single wind farm before we build it. Okay, this is a good comment from Rex Cat 180 again. It takes about an entire day on my laptop to get an accurate transit flows simulation for a simple aircraft with open foam. Yeah, you can just imagine how much more complicated a wind farm is than just an aeroplane. Okay, I won't answer more questions on the CFD because it's, I use it, but I'm not an expert, so I won't get into that too deeply. All right. From Alan Hall, leading edge erosion should be a big issue if trying to maximize layout. I think that's definitely true. Leading edge erosion is one of the big issues in wind turbine technology these days. It's still not solved completely well. And I think that I've seen research that shows that the layout of the wind farm can have an effect for, certain turbines are getting a lot of erosion and certain ones aren't. I think we're in the early days of properly understanding that, and I will expect that we'll see a lot more movement in that space over the next few years. Okay, so let's move on. So basically, we want to put turbines as far apart as we can, like in the, if the wind's coming this way, we want to put them as far apart as we can in that direction so that, no wind turbine is ever close to another one downstream. but they can be as close as you like across the wind. There's no problem there. So if the wind is always coming from the same direction, then that's no problem. You just line up the wind turbines in a row perpendicular to the wind direction, and it's easy. But as we saw with that windrows that I showed you, I mean, it's much more normal that you're going to see changing wind directions at a wind site. So the next topic that I want to move on to is how we can get around that, where how we can keep turbines as close together as possible, in the crosswind direction, but keep them far apart in the downwind direction. And there has been a few different interesting ways to do that that I've seen recently. So I'm just going to find this here. This is a paper on the Vestas multi-rotor wind turbine that they made. So what they did was they refurbished 4 small wind turbines. I think they were 225 kilowatts each, and put them they made this new structure with one tower and then, some support arms, and mounted them all on a single tower. They actually made this. They installed it in 2016. They looked at the results over, I think it was up for 3 years. And now we have these like actual measurements, which makes this a very, very interesting for me. So on their device, you could yaw the top and bottom layers separately, and they did that because sometimes you see the wind kind of goes in layers as you go up. So if the top and bottom wind turbines found themselves in different layers, then you could you could get each half of it still oriented in the most efficient way to take advantage of that wind. So I actually spoke to one of the engineers who worked on this at Vestas, Eric Carl Lanesko Miranda, and he was very generous with his time over the weekend to explain to me what they learned. But first of all, I wanted to show you, there is a video on it.
The multi-rotor concept demonstrator consists of 4 V29 turbines mounted on a support structure. And the support structure is basically just a tower with support arms. Each of the support arms can contain 2 V29 turbines, and each of the support arms are able to yaw individually upwind. The multi-rotor turbine is a concept demonstrator meant for investigating challenges. It is not a sales product. Over the last many years, turbines have grown bigger and bigger in order to harvest more power and reduce levelized cost of energy. But we want to investigate if we can scale down the turbines and still produce a cost-efficient turbine, reducing cost of energy and improving annual energy production. We also believe that the multi-rotor turbine could help us reducing the need for special transportation vehicles and tools. And in some markets, this is a very big advantage. We have basically identified 3 major technical areas we want to investigate with the multi-rotor concept demonstrator. And one is the structural dynamics. This is a structure we don't have any experience with, and we need to investigate if there are unforeseen vibrations in the structure. And moreover, we need to investigate the aerodynamics. We have rotors sitting quite close to each other, and we need to investigate how they interact with each other. And last but not least, we need to investigate how well our load models predict the loads on a multi-rotor turbine and adjust the load models accordingly.
Said what they were trying to achieve with this multi-rotor, and it was more trying to see what the limits are going to be. I know that they've mentioned that they never were really expecting this to become a commercial unit, but they just wanted to see, that you see these theoretical papers that show that there's some advantage from arranging turbines in an array, and they're actually have gone through and measured that and figured out that they found, new challenges, because every time you try something new, even if it sounds really simple on paper, if you'd like take this Vestas project, they've just taken 4 already existing turbines that were decommissioned, they refurbished them and put them up. So, it sounds like very simple. You're just reusing 4 turbines, but actually there were a lot of lessons that they learned about challenges that they weren't probably expecting. So yeah, it was a good learning exercise to see if this is going to be something to pursue further. So they did publish a paper as well, which if you're interested, then I would definitely recommend checking this out. So it's called Power Curve and Wake Analyses of the Vestas Multi-Rotor Diameter. It was published in 2019. And so they go through, I highlighted these parts because they referred to some interesting papers on what's happening with the wakes. And it goes through all of the different measurements they took. And then it shows where it was installed also in Denmark. And what I thought was interesting was, so this is a picture of the wakes. So you see the four little turbines here, and these ones here are actual measurements of the wake. And this is half a diameter back from the turbine. This is 1 diameter back, and this is 2 diameters back. So you can see how the blue colors are slow wind speeds, and the red color is like the free stream, the speed of the wind where there isn't a turbine in the way. So you can see immediately after the wind turbine, you can see, basically the wakes show up as like bluer colors, and then as we get further away, then it mixes better. But they were the first one to simulate the effect of the wake on a multi-rotor, but they were first ones to be able to back it up with experimental data. So basically what happens when you have 4 small wind turbines together, you've got the same swept area, the same amount of power as one single turbine with double the diameter of one of these small ones, but the wake doesn't persist as long. So basically when you've got the 4 small turbines together, then you've got more surface area, more perimeter, more, where the wake has the possibility to interact with the free stream wind. So there's more mixing that happens, and so the wake doesn't last as long. And that's basically the effect that they proved here. And they also found a 1.5% increase in power production from the interaction that the turbines had with each other. It's my understanding. I had to spend a lot of time digging into this because I wasn't familiar with this effect. I don't think it's 100% understood yet exactly why you see this increased power, and you see exactly how wake persists. I know we use in the industry this rule of thumb that you would normally keep 6 diameters in between turbines when you put them in a wind farm. And this shows that if you, instead of having 1 big turbine, you have 4 small ones, you could probably put less than that. So it's interesting for certain cases. For now, like I said, I talked to Eric, and he mentioned that for now they didn't see the potential to. They didn't see that there would be any cases where you would really want to use this turbine for now. He said that you would want to see rotors, you would want to use bigger rotors before it would probably make sense. And also you need quite a specific site with specific problems before we would see this make sense to use a rotor like this and other ones. He did mention that it was really important to keep the costs down, that you would want to be using a turbine that you already made. So that, like I said here, they used an old 225 kilowatt turbine, 4 of them. You wouldn't make a new turbine just specifically for this. He said you would, lose so much in your development cost that you would never, recuperate that money given the size of the market that they expect for this. But nonetheless, I think it's really interesting it's a way that you can, put lots of turbines closely together, but they will never be in each other's wake, right? Because they're yawing with the with the change in the wind direction. So for sites where we see that there is a constraint on the land, or maybe you can't get a big turbine in there because, road access doesn't allow it, this could be a way to solve those kind of specific problems. Okay, from Rich, the noise signature from a quad could be more acceptable than a single big rotor, more spread, less thump. I believe that they did measure that there was less noise, but I didn't focus on it, so I can't point to where that was, but I think you're right. So from Christopher Sylvia again, that does seem like a good idea, especially if they can make all the blades the size of a normal flatbed truck. And yeah, I think that will be one advantage. But Eric did mention that the actual installation is much more involved than it is for, when you're just erecting a single tower and then putting a single rotor onto it. That can be done quite quickly, whereas this one was it was a lot more on-site labor. So transportation will be easier, but the installation will be harder. So, like swings and roundabouts. And that's, I think, one of the reasons why he said that it's really going to be like horses for courses. This turbine will see sites with specific challenges, but probably not in general going to be ever, this is the best thing that's going to replace everything else. From Alan Hall, the load models for the multi-rotor would be really complicated. Yeah, that was one of the big points of this study that Vestas did, was to see whether their load models actually bore any resemblance to reality. So I didn't look into that a lot, but if you look in that same paper, then it does go through that. Mike Purdy, fair play to them for trying it. Can't be cheap. Yeah, absolutely. And I actually did think this is the kind of project I would have loved to have worked on when I was, working for a wind turbine manufacturer. It's really fun to get to, try a big idea versus what is a much more normal wind turbine development, which is, a lot more incremental, and you're staying safe. You're making something that that people are going to want. It's going to make energy a little bit cheaper than the one that came before it. Whereas this one was like, okay, let's imagine 10 years in the future when we just can't go any bigger, or we've run out of sites that are easy to access. How are we going to deal with that then? And I think it's not just Vestas that are doing stuff like this. I've never seen it so publicized, actually, something really out there like this from a major manufacturer. So I definitely also give kudos to Vestas for that. But everybody is thinking, 10 years ahead in the future, at least, because otherwise, by the time that the market moves there, you can't respond in time. So there is a lot more of this going on in the industry than people realize, but just that they don't have the reason to promote it unless it becomes a product that they want to sell. And I think I would like to do a video or maybe a live stream about some of the big technical innovations that have happened at the major manufacturers that, have actually resulted in, real advances in the industry. Because the difference between the major manufacturer and, like a startup, which we're about to go to wind catching in a second, Vestas have the money to fund this, right? They're not looking for investors to get in. So they don't need to promote that at an early stage. And all the other manufacturers, their trial that they did was just to learn something, that wasn't to, actually produce a product to sell. They're not promoting that, whereas a small startup company has to. They need funding. They don't have multi-million-dollar budgets for development unless they get investors on board. So I think that's why people get this impression that the major manufacturers aren't innovating, because you don't see it, because they have no reason to share it. And in fact, it's better for them not to, because if you take, like 10 really out there ideas like this, then at least 9 of them are probably going to go nowhere. And I think that would probably, companies don't like to show a lot of dead ends that they went down, even though innovation means that you are going down dead ends all the time. But you learn from it, and your next attempt at something will be better because of that. Okay. Oh, yes. Okay. Lots of comments like this. We can't see them. So sorry. I was talking about this one, I think, when I was saying all that. So, yeah. Then this one from John Paul Christian: what happens if a flock of seagulls or geese fly into it? Have they got a way to stop animals jumping into it or flying into it? So I haven't seen specific studies for this multi-rotor or any multi-rotor turbines, but I am planning, I'm underway making a video about wind turbines and birds, because that's an issue that's, first of all, it's very close to my heart because I am a bird lover. I have binoculars and a bird app, and I go out and I find new birds, see them for the first time and check them off. And I don't want birds to die from wind energy, and I don't want birds to die from climate change. So yeah, when you look at the data, the studies that have been done, we see that birds, buildings, cars are the main things that are killing birds. Birds do kill some, wind turbines do kill some birds, but it's like very, very tiny compared to those sources. So that's why I personally consider wind turbines to be beneficial for birds overall, because they're solving climate change, which is a much bigger threat to birds. But I will go more into that on a video on that topic. So yeah, RexCat 180 makes the same point that I just did. Okay. And Richard Newton, confirmed bird nerd. I don't know if you're saying that you are one too, or just calling me a bird nerd, but I'm totally happy to have that label. I will admit that I am a bird nerd. Okay, so let's move on now to wind catching. So this is the wind catching system. And it's an array of, I can't remember the number now. It was I don't know, 50 or 100 or something smaller wind turbines. When you zoom in, it looks like they're two-bladed wind turbines. So that's, that's cool. I'm a big fan of, not needing to have 3 blades on every wind turbine. It's in this giant structure, and you can see it here next to the Eiffel Tower for scale. So it's gigantic. As far as I can tell, it only exists in the form of computer simulations for now. If you go through their website, or I've got this, I think it's an investor presentation, this one, it is definitely full of the sorts of red flags that I like to go on and on and on about. I'll go through some of them now, but I don't really want to get into the details too much. I want to talk more conceptually. So they say it delivers electricity at grid parity, but I mean, it doesn't exist. They've never made one, so they don't know that. Scalability for future cost reductions. 1 unit produces enough electricity for 80,000 households. Same amount of electricity as 25 conventional turbines, which is only relevant if it's cheaper overall. So then this is the more interesting thing. Multi-rotor effect increases production. And when I first saw this, when my dad first sent me this link, I'm like, yeah, whatever. I kind of rolled my eyes. But now that I've actually researched it, I say, yeah, there is an actual multi-rotor effect, and we could well see increased production from this, or we might, if they ever make it, then we may see that. And yeah, this is how they plan to arrange a wind farm. And so you can see there are some good conceptual stuff here. So 1, the multi-rotor effect is real. 2, it is a way that you could get pack closer together offshore, which seems like we need so much renewable energy added. And I have seen some studies, talking about the wind capacity in the North Sea, for example, which is a really important site for Europe's energy transition. So I think that there probably is in the future going to be a need for, saving space in the ocean. And this is a way to do it. Because they've got these, the amount of power produced by each one of these units is big compared to a normal wind turbine. So that should see fewer connections, fewer cables potentially compared to a normal horizontal axis wind farm. So that's an interesting plus. Also, I wondered if the lightning protection of this one could be simpler than for a really, like maybe we're going to eventually see 150 meter, 200 meter long blades, probably with carbon fiber in them. Lightning protection is becoming a bigger challenge as blades get bigger and we add more carbon fiber. So I feel like this could be a better lightning protection concept. And then all of that it doesn't exist yet, right? It's just a model. I tried to get in touch with these guys and I didn't hear back from them, but I don't even know if I had the right email address, so I wouldn't put too much weight on that. So my comments for wind catching, it's like all of the details seem a bit weird. Like if I were them, I wouldn't be making it so big to start with. Maybe this is just, their artist impression of where they want to be in 30 years time. And their first unit will only have 4 rotors in it. That would seem like a more sensible size to start for me, because they're going to learn so much. I don't see it written on this presentation, but somewhere they've said it's going to have a 50-year design lifetime. It's going to have less maintenance than other turbines. All these kind of details that I think that they're going to be very surprised to find that it doesn't work out like that when they actually implement it. And it will be much faster for them to develop if they start small to prove it and then scale up. You do always see this tension with startups that, they need to do something impressive to get attention and get investment. I know it's easier said than done to start small and grow bigger, but from an engineering point of view, that would be good. And I also don't see any reason why they need to design their own little 2-bladed wind turbine. If I were them, to get going quickly, I would take an off-the-shelf small wind turbine and, focus on the real key technology risks, the things that they're doing that no one's done before, so they don't know what problems they're going to get. If they make their own wind turbine and they're not, an established wind turbine manufacturer, they're going to spend a lot of time learning how to solve these problems that most wind turbine manufacturers have probably already solved. So I would recommend, that would be a path through. So in terms of the details, I don't like the wind catching unit. In terms of the overall potential, I think it has some. So that's my impression on that. Christopher Silva is at a fixed or floating structure. I believe it's floating, and yes, the whole structure can yaw, or at least, well, actually, I think I might be assuming that. I think that was one of my questions that I asked. I didn't get answered, but if it can't, then no, there's no future in this. This is going to only work. Well, imagine, if the wind is coming like in this direction parallel, I mean, like nothing's going to happen there. It has to be able to yaw. Okay. So DK Shadow says, with wind, it's go big or go home. Economically, that is definitely the way that it works out, and we are seeing trends to get bigger and better. So, I mean, this and the Vestas multi-rotor, they're both aiming to go bigger without just continuing to, grow the normal 3-bladed structure. And I do think that we are going to need to see some sort of innovation like this at some point. I don't know when we're going to see wind turbines stop growing, but at some point, like when you make a wind turbine blade longer, the weight of it scales approximately like with the cube of the length, whereas the wind power only scales with the square of the length. So it's not for sure that bigger is better in terms of just making wind turbine blades grow. The reason why wind turbines are getting bigger is because of other aspects, like you want to minimize the number of connections and generators and, those sorts of things. Okay. Comment from Philip Sheridan, looks a bit flimsy. It looks like a computer simulation to me. It doesn't look like somebody, went through and calculated did structural calculations for that thing. It looks like they wanted to make a picture for investors, which, I mean, it's a reality that they need money. So I don't want to rip into them too much when they probably didn't have too much alternative. But yeah, it is a picture at this point. Yeah. Okay. Herman Rockholt says, in my opinion, it can't be turned. Therefore, it's big nonsense. I just can't believe that it can't be turned. It's so obviously total nonsense if it can't be turned. So, I mean, we'll see. We need more information. And yeah, maybe one day I'll get started on these live streams further ahead, so I have more chance to get in touch with everybody. But yeah, I would be really surprised if that can't yaw. Okay, so Herman Rockholtz again. Furthermore, in aerodynamics, bigger is better, and yeah, that's yes and no. It's not that obvious. I think there's some effects going both ways, and I'll talk about that more in a future one where I'm going to get a blade aerodynamics expert on, and we can talk about that then. Looks like a lot more materials per wind cross section. So this one, I mean, the amount of like the lattice structure, yeah, it's complicated, but at least, like easily transportable. But then again, the amount of labor to install that offshore is probably going to be more than a normal tower. And, that's critical how usually they're trying to really reduce installation time offshore, especially because it's hard to get people out there. But in terms of the wind turbine blades, you're going to use a lot less material for this design than you would for, a single rotor that has the same swept area. And that's because of that square cubed scaling law, which, it just because, you have such a big cantilever load when you make a really big blade, really long blade, you need to make it very strong to be able to support that. And definitely, I know that I need to do a video on how wind turbines scale, because that's a topic that comes up over and over again. I like this one. B Dykes, Rosie, you could do consulting for venture capital firms investing in wind turbines. Yes, I would love to do that. So please, everybody that knows a venture capital firm wanting to invest in wind turbines, get in touch with me and I will do your technology due diligence for you. So thank you, B Dykes, for advertising my services for me like that. Here's one from Johann Steinlechner. You're looking at vertical turbines come to Palm Springs, and you can see. I didn't know that is there a vertical axis wind farm, and when was it made? Because I know there was a lot of effort made on them in about the 90s, and I haven't seen any since then. But definitely keen to have a look at that if someone can tell me more details about it. All right, so yeah, I mean, like I said, I found this topic really interesting once I got into it, way more so than I was really expecting. There is definite advantages in these multi-rotor fan clubs, we're going to call them, lots of wind turbines collected together. So in the future, I do think that there is going to come a time when we are not simply just making the same shape of wind turbine bigger and bigger or longer and longer. I do think that at some point that's not going to be possible anymore. And in places where the land is constrained, which isn't everywhere, isn't even most sites, like I described at the start, but where land is constrained, I think that we are going to see more things like this. So wind catching, I suspect they're probably too early, but something like that, something like Vestas, I think we will see that. And so I find it interesting that, especially with the Vestas thing where they actually built it and actually measured, that's a really good starting point for, when the market conditions become such that we need to go in this direction. Now we've got a really solid foundation for it. So that's basically my my take on fan clubs, on groups of wind turbines. So I just wanted to thank again WeatherGuard for their kind sponsorship of this live stream. It takes a lot of time for me to do all the research to put something like this together, and I wouldn't be able to do it without them. So big thanks. And I also want to thank my Patreon team, the Engineering with Rosie Patreon team, who, especially for this one, really helped identify what are the interesting topics within this space. And in general, they're suggesting topics for the future. And we have a Discord channel where we discuss all kinds of interesting things that are happening in clean energy. So I want to thank them. That's all I wanted to say today. All right. So thanks for that. Thanks everybody for watching and for the good questions. And I've got the next topic I haven't quite settled on yet. I've got quite a few in mind. I want to do airborne wind. I want to do blade aerodynamics, including add-ons like winglets and vortex generators and stuff. I want to do batteries as well, the way that they're used, like the different business cases for batteries, maybe even different battery chemistry. but probably none of those will be ready for the next one. So if you have an idea for something that's been in the news, something that you've seen, some clean energy topic you've seen in the news a lot recently, and please comment on the video comment, not the live comments, about what you'd like to see. Yeah, and coming up in my normal videos, I've got bioenergy, I've got green certification coming, and also explain a video on the levelized cost of energy, which is a tricky topic to make very interesting, but I'm doing my best. Great. So thanks, and I'll see you next time. Bye.